In this lesson, we're going to work on generalizing the binomial expansion. And by generalizing, I mean working with exponents that could be rational. For example, here you can see we are expanding 1 plus u factors in the form. We're mostly going to focus on factors in the form 1 plus u to the alpha, where you can see that here alpha is in q, which means that the exponent is no longer required to be a natural number. In this case, it could be a fraction, it could be negative, it could be a negative integer, etc. Now, these types of expansions can keep on going infinitely. Now, as you can see over here, since it's not really that hard to remember, since we're working with factors in the form 1 plus u to the alpha, the first term is always 1. And the second term is always alpha times u. And as you can see that the exponent of u increases infinitely. The first term has u to the 0, which is constant, then u to the 1, then u squared, u cubed, etc. Now, regarding the coefficients, which we will discuss now in a bit, how these coefficients are obtained. But as you can see, there is a pattern here. So first we're starting with 1, then u is multiplied by alpha, now u squared. Now keep in mind that since the exponent here is 2, then at the numerator I have two factors, which are alpha and alpha minus 1, and the denominator is the exponent squared. It's the exponent factorial, so we have 2 factorial here. Now if we move on to u cubed, since the exponent here is 3, then the denominator and the coefficient is 3 factorial, and the numerator is consisting of 3 factors, alpha, alpha minus 1, alpha minus 2. And that pattern keeps on going. For example, the coefficient of u to the 4 will have a 4 factorial at the denominator, and at the numerator will have 4 factors that are alpha, alpha minus 1, alpha minus 2, and alpha minus 3. Now, how is this formula obtained? In fact, if we go back to the definition of the binomial expansion that you're already familiar with, where the exponent was in fact a natural number. Now, this was the binomial theorem, where alpha was a natural number here. Okay, so a factor in the form 1 plus u to the alpha is in fact the sum where r goes from 0 to alpha of the combination of r out of alpha times 1 to the alpha minus r times u to the r. And 1 to the power of anything is 1, so which simplifies the series into only having the combination of r out of alpha times u to the r. But notice here the difference between the regular binomial expansion, where alpha is a natural number, with this generalization of the binomial expansion, where alpha is in fact a rational number, is the fact that when alpha is in q, the expansion can keep on going infinitely. Usually in the exercises, the question specifies up to which order or up to which rank you stop your expansion. So here it's stopping at alpha because this is based on the binomial theorem where alpha is a natural number. But in fact, keep in mind that when alpha is in q, the expansion can keep on going infinitely. Okay, now let's just now discuss how the formula you see here at the top is obtained from this series. Now we're going to first work on simplifying the combination of r out of alpha, because that's the whole thing. Because you can see here I have u to the r, and as r starts from 0, you would have the constant plus u squared, plus u cubed, etc. So it's all about simplifying the term containing the combination of r out of alpha. So starting with the combination formula that you already know, which is alpha factorial over r factorial into alpha minus r factorial. Now you know that alpha factorial is the product of alpha by all its preceding terms all the way to 1. Okay, so it's alpha into alpha minus 1 into alpha minus 2 into alpha minus 3, etc. Now over here you'd notice that I'm stopping it at alpha minus r plus 1 into alpha minus r factorial. Now alpha minus r plus 1 is the term right before alpha minus r. And if we refer to a numerical example so that it's a little bit more clear for you, if I'm dividing 8 factorial by 6 factorial, you'd know that 8 factorial is 8 times 7 times 6 factorial. I stopped it at 6 factorial because I have the 6 factorial at the denominator. Okay, so over here having alpha minus r factorial at the denominator, so I stopped the product at the numerator at alpha minus r factorial in order to be able to simplify. And here, referring back to the numerical example, what comes before 6 factorial is the 7. So what comes before alpha minus r is alpha minus r plus 1. Okay, so this is where the alpha minus r plus 1 that you see in the formula comes from. So simplifying alpha minus r factorial leaves me with the product of this pattern that we were just discussing in the formula earlier. So over here, expanding the sigma here, you would have the sum of the terms in u, or the powers of u, multiplied by their corresponding combination, and of course replacing r by its corresponding value in each of the combination, you'd obtain the formula that we just discussed at the top. Now let's just put this into examples. Okay, so if we start with the first example here, you'd notice that I have placed the formula at the top of the slide in order for you to keep track of how the formulas are being built later on in the example. So over here I need to expand the following up to the term in x cubed. So as you can see here that they asked you to stop the expansion at the term in x cubed, so this is where you basically stop. Okay, now regarding this condition for the absolute value of x being smaller than 1/3, now this is just interval of conversions of the corresponding power series that we will tackle later on in calculus, so we're just going to keep this aside for the moment. Okay, so we're first going to start by writing this expression 2 over 1 minus 3x in the given form at the top, 1 plus u to the alpha. So we know that 2 over 1 minus 3x is in fact 2 times 1 over 1 minus 3x, which leads to 2 into 1 minus 3x to the negative 1. So over here, u is negative 3x and alpha is negative 1. So applying the formula up to the term in x cubed, the formula above, we will have 1, of course, as the first term. Then alpha is negative 1, u is negative 3x. So I do the corresponding substitutions. Over here, alpha minus 1, so negative 1 minus 1 is negative 2 over 2 factorial times u squared, as we already agreed here, u is negative 3x. Okay, similarly for negative 3x cubed multiplied by alpha minus 1, alpha minus 2, so negative 1 minus 2 minus 3 over 3 factorial. Now simplifying these coefficients, we'll end up with 1 plus 3x plus 9x squared plus 27x cubed, which, to go back to the expression given, we'd have to multiply by 2, which leaves me with 2 plus 6x plus 18x squared plus 54x cubed. Now this is regarding the first example. Now as for the second one, I'd also have to expand up to the term in x cubed. But over here I have the square root of 1 plus 2x defined for the absolute value of x smaller than half. Again, I will have to write the square root of 1 plus 2x in the form 1 plus u to the alpha. We know that a square root is an equivalence of an exponent of half. So the square root of 1 plus 2x is 1 plus 2x to the half. So over here, by comparison, we have u equal to 2x and alpha equals to half. So by doing the corresponding substitution, by considering 1 plus alpha times u, this is alpha minus 1, half, and half minus 1 is negative half divided by 2 factorial times u squared. Then alpha minus 1, alpha minus 2, half minus 2 is negative 3 over 2, and of course this product divided by 3 factorial times 2x to the 3. Simplifying the coefficients, we end up with 1 plus x minus half x squared plus half x cubed. Now you'd have to watch out for the negatives here, whether you have a negative inside the exponent, if the exponent is odd or even, or whether you're multiplying an even number or an odd number of negatives. So you'd have to watch out for the negatives here. So this is regarding the second example. Now, if we extend it a little bit further, and if we tackle this example that asks you to use the binomial expansion to show that the square root of 1 plus x over 1 minus x is equal to, so they gave you the final answer here up to the term in x squared. So you'd know that you'd have to stop your expansions up to the term in x squared. So we'd have to show that this is equal to 1 plus x plus half x squared. So first we'd need to start by writing our expression in the form, or in terms of factors, in the form 1 plus u to the alpha. Now we know that a square root is an exponent of half, so we'd have 1 plus x over 1 minus x to the half, which we know that a over b to the n is a to the n over b to the n. So over here, this is equivalent to 1 plus x to the half divided by 1 minus x to the half, which finally leads me to the form 1 plus x to the half times 1 minus x to the negative half. So we'd use the binomial expansion in order to write an expansion of each of these two factors up to the term in x squared. So if we go for the first one, 1 plus x to the half, using the form above. Now here u is x and alpha is half. So we have 1 plus alpha u, so half x, plus alpha times alpha minus 1 over 2 factorial u squared, where u here is x. So you'd see that I have a plus with an ellipse here because the expansion can keep on going infinitely. We just decided to stop it up to the term in x squared in this example. So simplifying the first three terms, we'd have 1 plus half minus 1 over 8 x squared. Similarly, 1 minus x to the negative half. Here, u is negative x and alpha is negative half. So using the same formula up to the term in x squared, we end up with the expansion 1 plus half x plus 3 over 8 x squared. Okay, so now that I have the expansion of each of these two factors, and in the expression we want to find the expansion to these two factors are multiplied, so what we do is multiply these two expansions. So over here, I replace in this product each of the two factors by their expansions, and I start expanding using the FOIL method. Okay, so I start by expanding 1 into all of these terms, then half x times 1, which is half x times half x, which is 1 over 4x squared. Now, half x times 3 over 8x squared gives me a term in x cubed. So we drop that term and the ellipses here because we don't want it. We want our final answer up to the term in x squared. Then negative 1 over 8x squared times 1 is negative 1 over 8x squared. And then starting from the second term, negative 1 over 8x squared times half x, that's a term in x cubed. Negative 1 over 8x squared times 3 over 8x squared, that's a term in x4. So these two terms, we don't really need them in our expansion, so we drop them here in this ellipsis at the end. We consider them part of that ellipsis that takes the expansion infinitely. Okay, so we only want the terms up to the term in x squared. So grouping similar terms together, we end up with 1 plus x plus half x squared, which what they originally asked us to show this expression is equal to up to the term in x squared.